Hello, everyone, and thank you for attending today's webinar, The Evolution of a Utility-Scale Solar PV Layout, Feasibility to Construction Ready. I'm Kelsey Misbrenner, editor with Solar Power World. Before we get started, there are a few things you should know. This webinar will be sent to all registrants so you can view it again. Slides and other helpful materials are available to view at any time via the resource window on your screen. Submit any questions related to this webinar in the Q&A window. We will try to answer these during the webinar, but if we don't get to your question, our presenters may reach out to you afterwards. And finally, if you're watching this on demand, you can still use all of these features. Let's get started with today's webinar, The Evolution of Utility-Scale Solar PV Layout. Today's speakers are Maxim Markovich, Head of Technology, and Ben Callum, Head of Product at PV Farm. And now I'll turn things over to Ben.
Thanks, everybody, and welcome, and thanks for joining us today. Before we head off on our journey, let's level set quickly on why layout is important and what type of layouts we're going to be talking about today. In the initial project lifecycle, there's several distinct phases you're probably familiar with, usually defined by the actors responsible for each of those. Starting on the left here, we have our engineers and developers and utilities. We'll spend a couple of years putting the scope together to serve the energy needs of the community. Then on the right side, we have the operations of that plant. The circles here are really scaled to the amount of days that are time typical for these, so you get some relative understanding of what goes into each of these. And of course, as we move upstream, we have the detailed design and the construction. However, despite the multi-decade implications of these projects, most of the critical decisions happen in this tiny window, this 30 to 60 days, which is really that RFP and kind of bid period. That dot, the tiny red dot here, is where is one of the most critical pieces of this life cycle, where all the stakeholders are coming together to define the project expectations as it transforms from that feasibility into construction and beyond. The window here that we're talking about is where the money changes hands, where contracts are written, and many of the decisions that will affect the lifetime of the project are established. And one of the most important kind of artifacts at this point is the layout. The layout's how parties communicate expectations. It's how they hope to identify and mitigate risks and challenges. It's also where they lock in their respective commitments and investments in the project so that things can proceed as smoothly as possible for the coming year and decades beyond. When we discuss layout today, we'll be discussing strategies to build the most comprehensive plan in this brief period of time to ensure that all parties can proceed confidently and deliver what they've promised to investors and clients alike. It doesn't mean that all these decisions have to happen in this period of time. But what we've been building at PV Farm is a system that allows teams to evaluate projects comprehensively and at the right level of detail to support these types of decisions so that all stakeholders can really feel good that their projects are set up for success.
Now let's talk a little bit about why does layouts change? Why does layouts evolve? So there might be quite a few different reasons, right? So including like goals, priorities change, vendor equipment changes, refinement of initial design assumptions, or maybe risk mitigation for the new items, or maybe newly discovered cost trade-offs, etc. But from the layout standpoint, all those reasons can be defined more broadly. So as utility scale PV farm project progresses from its initial feasibility study to construction, there is a continuous evolution in the quality, detail, and accuracy of the data available. So the real challenge in the preliminary phase isn't just about making very quick decisions or swift decisions, but also about grappling with the lack of data. So like on the left jigsaw puzzle. So you can see that when the project starts, we have many missing pieces or many unknowns or gaps in our knowledge. And let's say we don't have a terrain here, okay? So, and then as we go, in order to progress, we need to have some data. So we use, for example, Google Earth. So we build some assumptions. We use like a moderate or poor quality data resolution in order to build some assumption. Is this a good terrain? Is it a bad terrain? And then based on this, we produce some layouts. And as we go further, we can, we can ask for a survey. We can get much more detailed data. And those like we will get a high resolution data, and basically every such update might affect our layout and decisions about certain things.
As we begin our journey here through this evolution, we'll pass through a number of kind of phases. If you're into the Lord of the Rings, it could be the realms, or however you want to think about this. We'll start on the left here with looking at some of the equipment selection, and then we'll move into maximum DC analysis. We'll look at if we're not quite finding enough DC on our first layouts, where we might find others. DC elsewhere in the layout. We'll talk about some risk management strategies, and then finally we'll talk about a few of the many ways that you can polish the layouts. That's sort of taking, we have these general conditions for the whole project or across the whole site, but sometimes you have to refine these, or you'll have to refine these as you get into the kind of corners of the project. A couple things to note here about this is that sometimes these branches here, we'll follow this sort of as we go through the project. You'll notice that there's some branches. These represent, different ideas that we've tried, and we'll use this map to sort of follow our journey start to finish. But sometimes these branches are dead ends, right? This one doesn't continue, or sometimes in other cases, we have sort of multiple ideas that were fruitful, and those can continue and help us along our journey here as we move forward. Last note here is that all the analysis you'll see here today was done in our platform PV farm, and while a lot of these ideas aren't new, we think it's unique. What we do think is unique is the ability to iterate across these ideas really quickly and all in one place in a matter of hours, not days. So like all evolutions, let's start at the beginning, right? This is really the primordial soup of what you own, of the layout. This is what you own, minus really where you can't build, where you're not legally able to build. And this is sort of the first version of what we might call a layout. But it really doesn't answer any of the questions about practicality. Is this a thing we should build? Is it going to be cost effective? Is it going to meet my pro forma? It doesn't answer any of those questions. So to get going, we're going to start, with that first phase. How much DC can we fit on the site? The amino acid, or the basic building block, right, of all layouts is really the string or the table. What we've done here is kind of paint the project to see how much DC we could potentially fit on the site. Again, one of the issues though, which anyone familiar with the construction side of the process will be aware of, you can't really buy this, and it's not really practical to put that into the project. But we do see this does set the upper bound here. We have 533 megawatts DC for this 2,100 acre site. And that kind of sets the upper limit of what we might achieve as we go through this process. If you remember, our target here is 490, so we'll kind of reference that as we go through this. Now, the next step that we have, since we can't buy a string individually, or we have nothing to mount it on, is we're going to go and look at what some specific trackers. Let's talk. You might talk to your tracker OEM. You may have a good understanding of what the geometry of this actual equipment is, and you may want to play with a couple different types of trackers as you get into your site. What we're going to ask here is, now that we have, we know that there's some cost efficiency in a longer tracker. So I'm going to take a 14 string tracker, which comes out to 84 mods, and I'm going to lay that out across the site. And immediately, probably unsurprisingly, we're going to see a hit. Instead of being able to fill in all these little gaps here as we could with the tables, now that we've sort of applied this layer of reality, we're able to, we're going to see a hit, and we're going to start to see some of these gaps. So you'll see that our DC has now started to come down a bit. But there's a couple other constraints that we want to make sure we can layer into this process. The next one is we have to collect the energy somehow, right? So we have to pull that energy into blocks or into our inverters throughout the site. A lot of times when teams are looking at this kind of in the initial phases, you're going to, if the site's unknown or the boundaries haven't been defined, or some of the other information, as Maxime mentioned before, is not available, you're probably going to start with sort of this idealized block. It's this perfectly kind of rectangular or square thing. But as you can see, when we apply that to the actual shapes and the spatial implications of the site and our geometry, we're going to start to get a lot of variation. And the other thing that's really important to note here is that we are going to lose some DC because of blocking, right? That may be obvious, but as we lay this out and as we start to fit the actual energy production onto the site, we're going to see a slight reduction in that. So here's where we stand. We've gone through sort of the initial setup of the project. We haven't done a whole lot of investigation yet. Again, our target is 490, and our current capacity with the latest sort of blocked layout is sitting at 478. We have some work to do. We also know that there's a heck of a lot of design left. So, we want to try to get as high as we can before we get into the details here. So the first thing we can do, noting as we talked about earlier, when we went to the longer tracker versus the table, we started, we lost a lot of space in those sort of gaps. So what we can do here is we can actually play with a mix. You play with any sort of module or any sort of divisible number by the string. In this case, I've added a 60 mod tracker to the layout, and we can immediately see that I jumped from this 478 way back up to 533. This is actually almost the same capacity that we had with just the tables, and it's a pretty good indication that we're getting a nice fit. There's going to be some cleanup and some work to do as we go through this process, but you can see here on the left side, red being the longer tracker, green being the shorter tracker, and you can see how those have been interspersed across the site so that we can hit that energy target. The next thing we can try as well is inverters. We know from some experience that a mix of different block sizes can also yield some important gains. In this case, we looked at a 3600 and a 2500 kW inverter, and we blocked out the site to see how that might affect this. We did get a little bit of a bump here. We got about a megawatt out of that. But in terms of the complexity that may add to our project, this one's probably not going to be worth the squeeze as we go forward. We do have a healthy DC-AC ratio, and we're able to kind of proceed with this. But I think we're going to let this branch go here. This is one that we're going to hang on to because it's, again, not worth the squeeze. So one of the conversations we often have with folks in the industry about this is, okay, we've laid out the equipment, we've laid out the blocks, but how do I know that I have enough room for my site access? That's going to be the vehicle access to the equipment. It could be some of the maintenance activities that have to go on to the site, and there's a lot of detail that goes into the design of those circulation systems throughout the project. What we want to do for this first stage, just to set realistic expectations, is we're going to add in our north-south roads. You can see some of these don't, are probably not going to be our final road here as we go through the site, but it will give us. We can set, we can say, let's say every 1,000 feet, we're gonna put in an access road. In this case, it's our north-south road. That will give us a realistic expectation for how much space those roads might take up. When we get further down the design, as we'll talk about later, you can polish these. You can go from something that's, pretty kind of brute force here, this checker pattern, to design some really efficient roads. And we'll see how that might affect our design. But again, we're trying at this point to make sure that we have realistic expectations as we move forward and we get deeper into the project. Another study we can do, this is sort of our toolbox or our toolkit of ideas to potentially add DC to the site when we find ourselves under, is shifting the trackers. Now, as Confucius knew, there's no way to really do this. It's likely to add a lot of cost to our projects. There's complexity both in the building of this. There may be complexity from the wind exposure. There may be a number of different pieces that add complexity to my project. But this is sort of a relief valve, or can be a relief valve, where we are able to get some more DC it may come at a cost, but depending on what the project goals are, we may want to do that. In this case, we've been able to bump up significantly to 531. You can see, this is sort of a diagram of how that would work. And then you can see it over here in practicality. You can see instead of the sort of square blocks here, we're able to go and sort of follow the boundaries, start to move those trackers and squeeze a whole lot more in. Again, this is kind of a good metric for us to think about as we go forward. We know that we have a little bit of a release valve if we get stuck later on, but we don't necessarily have to chase that down at this point. We're going to probably stick with the 516. This is above our target, and we'll move into the next phase of the design.
So basically, Ben walked us through equipment selection, maximum DC analysis, and also he touched base on some important safety margins from a support roads standpoint. So now we're going to talk a little bit about civil analysis, or mostly about civil risks, because those are almost the most important ones in a very early project phase. So we landed with the layout with mixed trackers with overall DC capacity 516. And our target is for 490, and our target for annual production is 780,000 megawatt hour. Okay, so basically we will jump right away here. So we have a layout, okay, and we can actually try to identify immediately where are those high-risk areas. The key here is that when we define those high-risk areas, we usually define them by trackers. When you simply explore or observe the terrain itself, it's really hard to understand where our risk areas. But when we already defined a tracker size, we can actually place it on the terrain, and we can, we can define those problematic areas. And what's important here is that the different trackers, different lengths of the trackers will give you different problematic areas. Especially this relevant when people do analysis tables versus trackers or something like that. So there might be completely different results in there. So we basically place trackers. You can see those, like red zones. This is how we have the tracker slope above 10%. So that's let's say our maximum slope is 10%. So basically we have those high risk civil areas. In a nutshell, so we have 2,833 trackers, which means is around 108 megawatt DC. And so we have two options what we can do here. So first of all, we can remove them, or the second option, we can basically grade the area. We can do cut and fill for those areas, right? So remembering that our current DC capacity is 516, but we needed 490. So we have some room for basically trying to do not the full area of grading. So let's run through a couple of scenarios what we can consider here. Okay, so the first scenario, again, if we will just simply remove those trackers, we will jump. It will hit our DC. We will jump from 516 to 409, which is basically not enough for us. We need 490. Okay, and in this particular case, those boundaries you see here, they're kind of movable, which basically means that you can place trackers there if you want. It's just going to cost you, okay? And this is why we have a couple of options. We can actually try to achieve our 490 by placing trackers of some of those areas, or we can try to use fixed tilt system without actually using those high-risk areas. Fixed tilt system is usually done in a two-part rate. And despite the fact that row to row or pitch for the fixed tilt is higher, in general, the fixed tilt system gives more DC than the single axis tracking systems. This is why we can kind of squeeze some site area in order to get more DC. So if I go to the next slide, for example, here, so you will see that we used a couple of areas here. So this is the area number 1, and then this is the area number 2. So this is where we used fixed tilt system. You can actually see it in our main view. And with this combination of the fixed tilt and single axis tracking systems, we were able to achieve what you can see here, 492 megawatts DC. And but what's the problem with the fixed tilt system is that you cannot get as much energy as you would get if you were to use the single axis tracking systems. So because we got 690,000 megawatt hours, which is lower than our initial target of 780. So that basically means that this option was fun and interesting, but it doesn't suit us. So we go to the next one, okay? So in the next option, as you can see here, we decided to use some of the high-risk areas, right? I'll just jump back for a second to emphasize that we were having like this high-risk area, this one, basically those three, this one, and basically those two. So because we had a spare, I would say 100 megawatts of DC, we didn't need to actually kind of use all of them. We could just use a couple of them. And that's what actually happened in here. We basically grabbed this area, this one, and we populated it with trackers, which gave us 491.3 megawatt DC, which is above our target. And the energy production was 788,000 megawatt hours, which basically means that we hit both targets for DC and for the energy. And we can consider the second grading option. So that was the option A. And so now we're gonna go and check the option B. For the option B, we used this as exclusion zone, and this one, and then basically we fit with the trackers the rest of the site. If you can check on this picture, you can see that we basically, except those areas, we used the rest of the site, and we received 491.5 megawatt DC, and is about the same 788,000 of megawatt hours of energy of the production. So, but the difference is that on this particular slide we got less cut and fill. So basically, the first combination of high-risk areas was more expensive for us. So by placing trackers there, we would spend 2.6 millions. And then basically versus 1.9 millions with the same DC and the same energy, almost the same. There are very minor difference, but it's almost the same. So which basically means we're gonna continue further with the option B. And so the next step, when we already kind of define those movable basically boundaries, the places where we don't want to put trackers, we can go and start more in-depth analysis. So which is cut and fill versus piles optimization. So the key here is to understand the trade-off in between amount of dirt we need to move versus still tonnage we will get of piles. And so in a nutshell, the problem sounds like you can play with a couple of parameters. So you can play with a grading window, which means you can grade your site, let's say less accurate, but you will get longer piles, or you can grade your site more accurate and you will have a shorter piles. And basically the judge here is the cost and energy. So basically the way how it works is that we run a couple of analyses, one feet grading window, and then 0.5 feet grading window. And then basically we check what's going on with our piles, with our cut and fill volume. So that's one direction of comparison, but another direction which I also want to emphasize because of the data and of the data evolution we were talking about, as you can see in the horizontal direction here, we have two different grid accuracies, right? So at the beginning of the project, sometimes we have like a 10 feet grid size, which means we downloaded terrain from a Google Earth or something like that. And then we try to make some decisions based on this terrain. But as the project evolves, we might request survey, or we just get more accurate data. So we got, for example, in this particular case, the terrain with 1 feet grading window, with 1 feet grid size. And what it gives us, it actually gives us, it's quite interesting, because if you will see the grading window for the grid size of 10 feet and grid size of 1 feet, the difference in grading will be almost twice, while the pile total length of the piles, that's the parameter we used here, we didn't want to complicate it with showing cross sections, so we show just basically 336 thousandths of linear feet of piles, and then here 339, which basically the length of the piles didn't change much because of the grid the terrain, but the cut and fill changed twice, which basically means that by making decision about the layout at this phase, when you have this accurate surface or terrain and this one, there might be completely different trade-off and completely different decisions might be made, which is important to basically understand and be aware of them. So here, before and just a couple more words about the trade-off itself. I just will probably show you this picture from the left. So where we have a profile of the tracker on the existing terrain. You can see here how existing terrain goes, and then we have a proposed cut and fill, basically. So cut and fill. Basically the blue is fill, the red is cut, and then we have a gradient window, this white window, and so then the final gradient. So and basically in this particular case we can simply find the best combination, which will be the most interesting for us from a kind of cut and fill and piles optimization standpoint. So that's about cut fill versus piles optimization, and then we'll go further and we'll talk about layout polishing. So layout polishing is a phase where we already good with, let's say, main metrics or main numbers of our project, and we are happy to go and start improving certain areas. And by improving, I mean including exchanging those placeholders Ben was talking about from a north-south road standpoint when we need to build something more meaningful. So let's have a look at example here. Basically, we have this middle portion of our site, which basically was solved initially as a one global area, despite the fact that we have a couple of streams here. So as you can see here, we basically we got like three kind of sub areas which we can define independently, and we can try to go inside of each this sub area and do a little bit drill down and do a little bit of editing and polishing in order to achieve better quality of the circulation for the site, or in order to get more DC, squeeze more DC, or to prevent some bad, let's say, spots. So we're going to talk about it here in a second. So what's going on here is that from the left, we can see the option before polishing, and we can actually find quite a few problematic places here. For example, here, the block number 26 is splitted by the stream here, and which probably will make it hard to build or very expensive to build in order to connect those leftover trackers electrically to the rest of the block. The same situation is happening here on the block 29. We get the same situation, and then we also can see some free space here, and again block 16 is also separated by the stream. And we can see also some other minor places where we would want to have an improvement. And also on top of that, we have a couple of situations when those roads we built as a placeholders initially in order to save some space for DC, in order to basically balance our DC and our target, we can actually also talk and kind of build them up a little bit better here. So from the right side, you can see a polished layout. But first of all, there is no basically exchange for the block on this stream, and also there is no problems here. Then this area was quite isolated, and basically we have block 18 and the road basically access and the road here, and the same here actually the entry point to the lower side of the site from here, and basically have the support roads 1, 2, 3, and then basically you have kind of equipment roads or east-west roads in that case with hammerheads at the end. So basically roads are connected in a meaningful way, which means that the equipment, the vehicles that basically responsible for maintenance of the trackers and the blocks, they can easily circulate here and access pretty much everything. So the same is achieved in the other areas. So and this is how we basically literally found on the site 8 additional megawatts DC, and by doing that we also decreased the total area of the road for the site. So that's kind of what we call blocking and rods polishing improvements. And again, as you see, the boundaries, they stay the same. We just basically did some polishing, as we call it. So let's go further. So the next type of polishing, or the next type of consideration we want to talk about here, is the medium voltage wiring. Because sometimes the question about where we can place substation can be open. It's not always open, but in some projects it can be open. And basically, it's quite important to consider a reasonable amount of scenarios in order to find the best spot. And usually, when we're talking about medium voltage wiring, the whole story is about grouping blocks together in the so-called medium voltage circuits, as you can see here. Basically 6 blocks, they were grouped together, and then the wire cable, it basically connects all of them, and the connection goes all the way to the substation. Okay, so that's the whole point of the medium voltage wiring. And then by doing that, we can actually appreciate different, let's say, so-called optimization problems or optimization biases. So first of all, we can build those paths for the wiring in a way to minimize the total length or total volume of the wire cables. The second way is that we can do this design in order to minimize the total length and the volume of the trenches. For example, you can see the option A or option B here. You can see that there are quite a few medium voltage cables go to the substation, and while on the option B, less trenches here, you can see that there is one trench literally. So, which basically means all those circuits, they go into one trench, which make it wider and basically affects the cost. This is why when we compare those type of scenarios, again, we use the 2x2 matrix. We can see A substation position, we can see B substation position, and then we can see different optimization bias, less wire, less trenches. And then we have basically medium voltage cables cost, trenching cost, and then the total cost for each of the options. In the real life, there might be many more options. But basically from this simple analysis, we can conclude that the most cost-efficient option would be option A, by placing substation here and by doing a little bit more trenches actually than instead of doing like one big trench. And it will give us cost savings as the total cost. So that's a simple visualization of how trade-offs understood and made. And as you see here, in the most cases, the judge is the cost or energy, or sometimes both. So in the real projects, the matrices, they're bigger, but the main idea is the same, basically. So here we hit into the next slide.
So kind of recapping the journey we've taken today, we started with our sort of paint by tables at the left side to see what we could potentially bound the upper limit of DC on our site. We started to apply some constraints. We applied some trackers to the site, some specific length trackers. Then we went and explored the blocking. We looked at different inverters and decided that that wasn't going to be a great option for us. We looked at different tracker lengths, which got us back to our target, over our target DC. And we progressed here to add in some constraints or placeholders so that we could, with confidence, know that we were going to be able to hit those targets, even when we layered in some of the more detailed items, such as site circulation or access roads. We looked at a really interesting example, mixing fixed tilt, but it didn't hit our energy target. We looked at a couple different areas here where we decided maybe we won't grade these, maybe we won't place any trackers there, and we did some cost analysis to select the best, the winner in that example. Then we went and explored different grading strategies to figure out what level of precision we're going to look at, both from an operations standpoint or maybe from a data input standpoint. And we looked at how that might affect our overall pile costs versus the cut and fill requirements. Once we did that, we dove in to look at a few different sub areas that had some problematic or less desirable areas of the layout. We massaged those, polished those, and brought them back together to do some exploration regarding the medium voltage or substation system location. So the thing we want to emphasize here, we spent, this is one presentation, a brief sort of overview of one of these journeys, but we want to emphasize that the journey doesn't stop here. You can go into any of these areas at any point and break them down, massage the areas or the aspects of the design that may be less desirable, and then bring everything back together and readdress the global. So want to thank everybody who's joined us today for your time. It's really a pleasure to kind of present this journey with you all, and we're really thankful for everybody. Well, I think we have time here for some questions, so we'll turn it over to the moderators.
All right, great. Just a reminder, you can still submit questions in that Q&A window. All right, first question, when does PV Farm plan to integrate terrain following trackers to this system?
Ben, do you want to take this one?
Sure. What I would say is if you're looking for some holiday gifts, you might want to get in touch and see what we have coming later this year. Short answer.
Great. Next question. What does the minimum maximum cut fill of 200 to 300 feet mean? Are we going to cut or fill 200 to 300?
Yeah, I'll take this one. So I'll push some slide to the audience. So basically, if we will go a little bit back here. So on this specific side, we basically showing explicitly how much cut and how much fill we got. So on this basically options, we try to achieve net balance. Basically, we try to got the same cut, the same amount of cut as fill. Basically, if I'll go one step back here, so that's the legend, because we have a bunch of different, I would say, visualization charts. For example, on this particular one, you can see that this is the middle area when no grading is happening, and so the red is cut. Everything that goes here is cut. Everything that goes here is fill. So this legend is highly configurable. So you can define the amount of ranges, and you can define you can see the share, the percentage, the area, and there are many more visual basically explanations and explorations of how it's done. Thank you. Good question. I'll go back to the last slide.
All right, great. Next question. It seems like all techniques you present also apply to what you call sub areas. Can you talk more about this process?
Go ahead, Max.
Yes. Yeah, sure. So the whole point of the sub areas is that we do understand that first of all, when we started to work with our users, with our current customers, is that quite often people need to use different settings for different parts of the layout. And inside the current software available in the market, it's a big challenge, and it's quite difficult to achieve. It's usually one global setting, and then you got final layout, and you do what you do. But the whole point of those sub areas was actually to have this opportunity to drill down in a specific area, to apply different settings, to polish it, or to change something, to change the modules, to change the trackers, to change blocks, to do basically all the changes that you can do available for the whole site, but in this small parcel. So, and that resonates really well, not only with the layout modeling, but also with cut and fill. You can have a different geology in one place. In another one, you can have a different pile reveal because of the flood zone, or you can have other different settings. So if basically, it's probably a long answer, but basically the point is that the sites are big and they have different conditions. And thus we need to have a tool which will help us to apply different configurations for different parts of the site. That's the point. Thank you. Great question.
All right, next question. I saw DC to AC ratio in some of the layout images. How was that calculated?
Sure. I'll take that one. So in our system, we're able to look at kind of all the detail across the DC collection system. So that's going to include the cabling and any losses associated with that. However, the DC-AC ratio in this particular case is really kind of the nameplate ratio. For each of the inverters that you place into the layout, you're able to see the inverter loading ratio, and you're able to get a real-time tally of what that ends up at a site level.
Thank you. Next question, are PV farm layouts exportable and in what formats?
Yeah, great. I'll take this one. Great question. So we can export the layout to AutoCAD or Civil 3D. So that's not going to be a 3D model, but that's going to be a 2D layout, which people can continue to polish in order to produce a construction drawings, design 60%, 90%, and further. And also we work with PVCs, so we can export shading scenes, so we can basically run equipment placement, or you can place your trackers or fixed tilt tracking system on the terrain. You can export it as a shading file to the PVCist. And also all the information regarding schedules, specifications, all the numbers, basically electrical, mechanical, civil, they're exportable into CSV or Excel file format in order to continue building some type of the story for the client. I guess it's important to mention as well that also if you do grading or if you do cut fill analysis in our software, the final grading terrain can be exportable as well into Civil 3D for basically continuous evaluation. I guess that's all there. That's pretty much, yeah, that's all about export.
All right,
Thank
great.
you.
Next question, what is your process for solar module supplier and size selection?
So I guess represented in the platform is, we work with pan file format, so you can bring those very specific or including all the electrical properties. You can bring those solar modules into the platform and place them on racking systems, which are also configurable. In terms of the selection of the module, we're not really involved in the kind of market analysis and the capacity analysis, but we do have a lot of customers that will come and say, hey, we did this layout with a 580, and now we have a higher output module, and we would like to swap it out, and we can accommodate that very easily.
Thank you. Next question, how are you calculating cost deltas?
Do you want to take that, Max?
Okay. Yeah, I'll take this one. So basically we have so-called catalog, or we call it also equipment database in our software, which basically we can add rates to every equipment we use. So to trackers, combiners, string inverters, central inverters, transformers, fixed tilt systems, also wiring, trenches, rods, and stuff like that. But on top of that, we also have an opportunity to add some other cost categories in the cost model, like general conditions or any other specifics, not related to the quantities in the model. So combination of those two factors gives us opportunity to calculate a good enough cost model for the comparison purposes. So for example, in the analysis you saw about piles and cut fill, we, for example, don't take into account geology, and basically that basically means that our pile length is not super accurate. But by having the let's say robust cost model, we still can compare easily option A and versus option B, and we can answer the question which one is more cost efficient. The absolute cost might be different, but the comparative cost will be accurate enough to make a decision about which option you would basically push further. Good question. Thank you.
All Great, thank you. Next question, was all of this analysis completed in one tool, and how can we try this?
Ben?
Yeah, love that question. Head over to pvfarm.io or hit the QR code that's on the screen currently and send us a note. But yes, all of this was completed, including the energy and the cost, as we've talked about, and all the other components to it. Thanks for the question.
Another person was wondering about the terrain following technology. If you wanted to reiterate your answer there.
Yeah, I just say get in touch with us, and we're working hard on that. We know it's a priority, and there's a lot of questions out there in the industry. So let's chat and see when we might have available what you're looking for.
All right, thank you. And then the next question, can PV Farm take into account ground frost conditions for pile lengths?
Yeah, that's a very detailed question, I guess, from someone who working as engineering consultant or something like that. So we don't take into account the geology for now. We basically, our pile reveal and pile abandonment are user inputs. So basically, let's say you're doing grading or cut fill analysis versus piles. You basically set up an area where you define the reveal and the embedment. And so then you basically do this analysis, and those inputs are come from the user. So the embedment analysis should be done outside of the app at the moment. So we don't do that.
Yeah, I would say,
but that's partially the reason why we have those sub areas, because assuming that on the layout you will have many different areas with different embedment because of the geology. And you can amplify those different embedments when you're doing cut fill analysis, so which will kind of give you opportunity to compare this anyway. But the actual calculations, structural calculations, we are not doing them, except one probably thing we do: wind load positioning for the trackers. That's the only one type of structural calculations it's related to structural calculations. That's the only type what we do.
So in other words, going back to what Maxime, his sort of the layering on, or the sort of as new information becomes available, you could start with a assumed pile length for the entire site. And then as that information comes back, as you get more cores done, or as you get more information about the site, you can break those down into the sub areas and apply those different settings. So there's a lot of flexibility to carry that design forward.
All right, great. Those were all the questions that we have time for today. If you have additional questions, please feel free to contact our presenters on your own. This webinar will be shared with all registrants, so you can view it again at your convenience. I'd like to thank Maxime and Ben for being here, and PV Farm for sponsoring today's webinar. And thank you to everyone in our audience for participating. I hope you enjoyed our presentation, and we invite you to join us for more Solar Power World webinars in the future. Thanks, everyone.
Thank you.
Thank you.